Welcome back. I realized that I didn't have a single example of an elliptic curve or a finite field in the previous talk, in the previous lecture about elliptic curves over finite fields, and there were no examples. So I just wanted to give one example and discuss a couple of interesting things that come out of this. So remember that the Hassa bound gives you an estimate. We had a heuristic last time that the number of points over k should be about q plus 1 points. And the Hassa bound, what tells you is what is the error of that heuristic estimate. So it gives you that at most, so it's about, this actually tells you that the number of points on an elliptic curve is bounded between q plus 1 plus 2 times the square root of q and above, below by q plus 1 minus 2 times the square root of q. So in order of magnitude, is about q plus 1. That's the right order of magnitude, and then the error. Okay, so here's an elliptic curve that I'm going to be working with. So y squared equals x cubed plus x. That is an elliptic curve. I'm going to define it over fp, the field with p elements, and I'm going to choose p to be an odd prime. Why? Because if you look at the discriminant of this model, the discriminant is 64, or minus 64 rather. And well, if p is 2, then the discriminant would be 0 modulo 2, and that is not an elliptic curve because that would be a singular curve over f2. Okay, so that doesn't define a curve over f2, but since the discriminant is minus 64, this is non-zero if p is not 2, and therefore it defines a non-singular Weierstrass model for an elliptic curve over that finite field. So now what I'm going to do is change the prime and see what happens as I modify the prime. So, so here, for example, what I've done is compute for p equals 3, how many points are there? I can just check every x value and see if there's a corresponding y value. So it turns out that all the points are those. There are exactly 4 points for this elliptic curve. And then just check that the Hassa bound works. The Hassa bound tells you that it should be about 4 points. So this is actually on the spot, right on. It is 4 points, so the error is 0, and it is within the bound that Hassa gives you. With p equals 5, we actually also have 4 points. You can check that those are all the points. And now the bound tells you that this should be about 6 points. So we are a little bit deficient on points. So the difference is minus 2, and absolute value is 2, and 2 is less than the given error that Hassa gives you. Okay, you can do this. I've actually computed a bunch of primes. I wanted to show you how I did this with magma. So if you define a field with 7 elements, so that is GF7 gives you a field with 7 elements, and then define K to be that field, I can define an elliptic curve over K by putting coefficients in these are the Weierstrass coefficients. So this is A1, A2, A3, A4, and A5. In our example, the only coefficient that is non-zero is A4, which is 1. So I put, what this means is the coefficient is 1, but I want it to be 1 living in the field K. So K exclamation point 1 is yelling at magma, it's in K, okay, just so magma realizes that it's in K. And that defines E to be an elliptic curve over K. So there it is. And then you can do things like how many points are there on E? There are 8 points in this case. How many were we expecting? We were expecting 7 plus 1. So it is another case where it's the number is right on. It's exactly 8. You can actually find all the points on E, and here is all the points. Those are points in projective coordinates for E. We can replace 7 by another prime, say 11, and then compute. Again, I have to redefine E to be now over that field. And now, how many points are there? Now there are 12. 11 plus 1 is 12. Again, it happens to be exactly the same number. There's a reason for this, because this elliptic curve is special. It has complex multiplication, and there is a reason why these primes are exactly, the number of points is exactly 2 plus 1. And I can find the points again if I want to. There are all the points on the elliptic curve. Okay, so that's just a little bit of magma right there. And what I've done is, here is a table of, for this elliptic curve. It's still same elliptic curve. I've computed for each prime up to every prime below 30 what happens. And well, you see that 2 is bad. Well, that doesn't look good. 2 is bad, so I'm not going to do anything with it. 2 is what we say is a bad prime, because when I try to do, when I look at the discriminant, it vanishes. But for all the other ones are good primes, and I've divided them in 3 categories. You can see that in green, I have those where the bound is exactly on, right on. So it's exactly, the error is 0. And orange are the primes that are deficient in terms of number of points, and in blue are primes that are that exceed the bound. All right. So you can see, if you start looking into this, you might realize what happens, what is happening. There's a lot of patterns that one can deduce from here. One thing that I wanted to point out is this prime, where you see that the bound is 10.77. So that means that the difference between the number of points and q plus 1, the error can be at most 10, because those are 2 integers. And in here, in absolute value, that is exactly what happens, okay? That I have that the error is exactly 10 in absolute value. So we call that a maximal prime, but it's just an example that shows you that the Hassa bound is best possible. Okay, that error given by the Hassa bound can actually be attained. You can improve this Hassa's theorem trivially by putting the floor of this function there, right? And that's what happens here, that the floor of this number in absolute value, that is exactly minus 10. Yeah, that is exactly 10. I don't think I did those absolute values right. Let's put more absolute values everywhere. Okay. All right. But a couple of directions that I felt bad I didn't mention, I didn't use my opportunity to mention, is that, so these numbers are called AP, and they are called AP, I guess it's minus this. P plus 1 minus the number of points are called AP. And those are what's called the trace of Frobenius, it's called. That we already saw for what Frobenius refers to here. Frobenius is the Frobenius endomorphism, and you can write a determinant for it. You can write a matrix form for it, and then the trace of that matrix would be actually this number, the trace of Frobenius. So it is an actual trace, like in the linear algebra sense. And when you study these numbers, what happens for an elliptic curve? There are 2 directions that you can go to that are both extremely interesting and have produced a huge amount of research, which is, one of them, still conjectural, is that, well, so look at all these numbers, and you can ask yourself what Birch and Sinnerton-Dyer ask themselves. So in the 60s, Birch and Sinnerton-Dyer had this in principle, like a simple idea, which is suppose that you have, that I'm considering my elliptic curve over Q, and then I'm going to do all my reductions modulo P for every prime, like I did in this table, and see what happens. Then their thought was that if the rank, remember that we are going to prove the Mordelve theorem that says that this is torsion plus some copies of Z. If the rank is high, so the rank is large, then there should be a lot of points that, as long as the denominator is not divisible by P, those rational points, I should be able to reduce them modulo P and get a lot of points mod P. So if the rank is high, does that imply that, so if the rank is high, does that imply that the number of points is large? How large? Well, Hassa tells you what the bound is, but is it true that this is very often bigger than P plus 1? And they started studying that, or not for all the primes, but maybe for many primes. And what does, the question is, what does it mean very large, and what does it mean many primes? And putting all that together, they came up with what we now call the BSD conjecture, the Birch-Newton-Dyer conjecture, which hopefully we will talk at the end of the class, at the end of the semester. I'll talk more about this in terms of like building the L function and stating what the theorem actually says, or not the theorem, the conjecture says. Okay, so that is one direction. The other direction is the following. So you can write the you can write Hassa's theorem in another way. Hassa's theorem tells you that if I write P plus 1 minus the number of points, which is the trait of Frobenius, I can write it as a number that is 2 square root of P, that would be if it was the largest, times a cosine. We can write it like this, and it's somewhere that's going to tell me now, with the multiplying by a cosine, it's going to tell me that that number on the right changes from minus 2 square root of P to 2 square root of P, depending on what angle theta P is, right? So it turns out that if you look at the distribution of those thetas, you find out that the distribution is really nice. There is a probabilistic distribution that appears for all the elliptic curves. In fact, there's 2 types of distributions. Elliptic curves like this one with CM are going to have a distribution. Elliptic curves without CM are going to have another distribution. So, but it turns out that if you look at the probabilistic distribution, then you come up with what's called the Sato-Tate conjecture. That tells you exactly what that distribution should be. Okay, and amazingly, this theorem was proved by a number of people. I'm going to forget some names if I try to name them all, but there was a proof first with some mild conditions in 2008. In 2011, this was proved, and actually not just for elliptic curves over Q, but over totally real fields. For totally real fields. Q is a totally real field, so if you just want elliptic curves over Q, you have a proof. So that distribution is actually known. And now there's a lot of other generalizations of Sato-Tate. We look at the same kind of thing, but for abelian varieties, and that is not known in many cases, but we have conjectural lists of what distributions happen and when they happen for several types of abelian varieties. So there's a lot that one can say just from Hassa's bound. A lot comes out of it, and at the very least, we will come back to this. Okay, we will come back to the Birch-Newton-Dyer conjecture later on. But before I can state it, I need a lot of terminology first about SHA and about the regulator and things like that. So we'll come back to it at a later time. All right. So
can I ask a quick question about the bound before we continue? Thank you.
Go ahead.
So obviously this example tells us that this bound, at least the floor of the bound, is a best possible in the general case.
Yes.
Are there certain, can we make certain restrictions on primes or certain restrictions on elliptic curves that allow us to have a better bound? Like, are there sort of special cases where we get a better bound than the Hassa bound?
No, I believe that's a very good question. I would have to look this up. I believe there is always maximal primes. If you give me any elliptic curve, there will be maximal primes. And I believe there are papers about the distribution, how many maximal primes there might be. And I think what you can do is find elliptic curves that have more maximal primes than other elliptic curves. But I believe this bound is always the most efficient bound you can find for any elliptic curve. I believe. Okay, I'll look into that. But yeah, yeah, I think it's as efficient as it gets.
Okay, thank you.
Yeah, thank you. Right. So yeah, let's stop here, and then I'm going to continue with another video on elliptic curves over the complex numbers.